Hello and welcome to today's lecture and exercises in online floatsat. Today we're going to start a series of introduction to rodos. Rodos is a real-time operating system that we will use in our course. The first question that might arise is, why do we actually use a real-time operating system? You could also implement your onboard software without an operating system. That means that you plainly develop on the hardware. You have, for example, a giant loop and where everything is done there. So we have a system that has to accomplish several tasks. And those tasks should run quasi-parallel. And those tasks have different timing constraints. So for example, we might have our attitude control, which has to meet very specific timing constraints. So you have hard timing requirements here, but you could also have tasks that might not be that time constrained. For example, we want to calculate some navigation that should be done in the future. So this can step back from being processed and give the attitude control time to do the attitude control. And this is what I mean here with the priorities. So we have different priorities that define which task should be run first. And this is where dynamic scheduling comes into the play. If you have static scheduling, you definitely define which task should run when. And with dynamic scheduling, this makes it more flexible. So due to the priorities, we still make sure that high priority tasks are run first and low priority tasks are run later. And if we have free CPU time on the processor, for example, some tasks might suspend due to waiting for an input. In these times, other tasks can be scheduled dynamically. So for your development tasks, you don't have to bother about the scheduling. So you don't have to build a static schedule. You just implement your tasks, assign priorities and timing constraints to them, and everything else is then done by the real-time operating system. Another advantage is the hardware abstraction. So you develop on a desktop computer, for example, but you want to run your final software on some target hardware platform. And you don't want to test your software every time on the hardware platform. Maybe you want to test it also on your desktop computer where you develop the software. That means that the software should run on both systems, the desktop computer and the target platform. And this is where this hardware abstraction comes into play. So it defines some hardware abstraction layer against which you program your software. So there is an API that is common for all platforms. You program against this API, and the hardware abstraction layer takes care of translating the API calls to the appropriate hardware instructions. This is the clear programming interface. But this clear programming interface is not only towards the hardware down. We also have a clear programming interface, for example, for communicating between tasks, or a clear interface of developing new tasks. So you have an interface for threads and so on. And these clear programming interfaces and communication mechanisms make it possible that you can divide your program into separate parts that can be developed independently. So you have your programming team who can split up the software into different parts. The only thing you have to do here is to define the communication interface between the different parts very, very well. After you have done that, every programmer can program their own parts, and if they are finished or during development, you can fit them together at the communication interfaces that you have defined before. So these are the advantages of a real-time operating system. There are several of them, and we are using rodos, which is a real-time operating system. rodos stands for Real-Time Onboard Dependable Operating System, and it has a preemptive dynamic scheduler. Dynamic scheduler we already mentioned before. That means the scheduling is not necessarily predefined at compile time. Instead, the tasks are scheduled dynamically at runtime. And the preemptive part here means that rodos is capable of suspending a thread while it runs. So the task, the thread, does not notice that it is suspended. So it's just suspended by the scheduler, and it is resumed afterwards as soon as the scheduler executes the task again. The only thing where task can notice is if they have a look at the time. If they request the time and they see, okay, there is a lot of time passed between the two requests of the current time, then they might notice that they have been suspended. But for the normal run, so you just implement your task one step after the other, and you won't notice if it's suspended, preempted by the scheduler. rodos is mostly written in C++. There is some small assembler part for the low-level hardware implementation, but the API from your application towards rodos is everything written in C++. So it provides a C++ API that also highly uses the features of C++, such as classes and inheritance. We will see later at the details. It supports different platforms. On the one side, bare metal platforms that mean that rodos directly runs on the hardware. So, for example, on the Raspberry Pi, on discovery boards from STM, Smart Fusion 2, Geckos, and some others. And on the other side, rodos is also capable of running on existing operating systems. For example, on POSIX operating systems, such as Linux, for example. This makes it possible to develop and run the application on your desktop computer, but you can also compile it then on bare metal and run it on the target platform. And this is the basic build-up of rodos. So we have down here our hardware platform, our target platform. We have our hardware abstraction layer down here, our kernel, so that is independent of the hardware. And on that kernel, so this is the API here, up here. This is where your applications program against rodos. So, and this upper part can be moved from one platform to the other, and also on Linux. And you don't need to change your applications at all. Okay, no, that was the overview. Now let's have a look into rodos. At first, let's have a look at the file structure, the directory structure. So I'm going to switch to the virtual machine that you have already downloaded and run. So first, let's start our IDE. So with double click on Eclipse, So on the left side, you see the file structure. So I'm just going to open the folder rodos, which is the folder, as the name suggests, which contains rodos. We're just having a look from top to bottom and see what's in this folder. So the most important folder for your programming is this API folder. This API folder contains all the header files that you can use in your applications. At the first place, the most important one is the rodos.h file, which is the header that you include into your application. And this header rodos.h file does nothing but including all the other header files that are usually used for a rodos application. So that means in your application, you just include rodos.h and get everything available. So if you have some questions about implementation or API details, just go ahead and have a look here. Most of the files here have very good documentation as comments, and you can have a look there. For example, we're going to use the threads. You can just have a look. It's quite easy. So the source code of rodos is quite easy to understand. You just can have a look here. Yeah, basically that's it. So there are two subfolders. One is for the hardware abstraction layer. So it defines interfaces toward hardware devices that then are implemented dependent on the hardware in the CPP files we will see later. And then we have the gateway. This is part of the communication middleware. We will have a look in a later lecture. And if you want to use the gateway, then you can include this one. But we will have a look later there. So then the build folder is some intermediate folder. You don't have to have a look there. So this is where rodos is built. We won't have a look here, so it's not important for you. Then we have CMake. So rodos can be built in two different ways. The first one here is CMake. That means you can define your own CMake lists files that define how your program is built. So for example, which source files to include, which defines to set, and so on. And you just include a rodos as a subdirectory here. And then you can add a rodos executable that has a name as a first parameter and a list of CPP files at the end. And of course, you can define several CPP files in a row. You can also some test CPP, my files, CPP, and so on. So it's not limited here. But we keep our hello rodos here at this place. And this folder here, the CMake folder, contains the CMake files that are used for compiling rodos using CMake. So some general CMake here. And we have also some ports. So these CMake files are only used for specific target platforms. So and these are then used as a CMake toolchain file. How this works, we will see later. Okay, so then the next one here is the doc folder. Here we have some documentation files. So if you want to read further into detail here, just have a look here. So we have an intro to rodos documentation, coding directives, and so on. So if you're interested, don't hesitate to have a look here. Then we have a scripts folder. It contains different scripts. The most important for you are the build scripts. So I just have mentioned that there are two ways to build rodos. One is the CMake and the other one is the build scripts. So that means that you go on the terminal and use the scripts to directly build rodos. How this works, we will have a look also later. So just let's keep on looking at the folder structure here. So the source folder here is where, as the name says, the source code lies. So apart from the API, so the API only contains the declarations. That means the header files. Here we have mainly the implementations. And this source folder is divided into different subfolders. The first one, bare metal, contains all the port-specific code for the different target platforms. So that means if you compile your application for a specific platform, only the content of the platform is used for the compilation. So for example, if you compile it bare metal on Linux, you can also compile it for the STM32, which is used in your project. That means that all those source code is taken into compilation. You see, we have different hardware-specific code for the UDP, for example. We have the HAL implementation. So this is the implementation for the hardware abstraction layer of rodos. So for example, if you want to use the UART, this code is used. Usually you don't have to dig deep into this folder. So this is just the specific code of the target platform. Then we have bare metal generic. This contains code that is used for bare metal compilation, so not on a guest OS. But this code here in the bare metal generic folder contains code that is used for all bare metal ports. So for example, the scheduler, our preemptive dynamic scheduler is implemented here. On guest platforms, the native scheduler is used, for example. And we have an IP stack also here. Then we have independent code, which contains code that is used on all platforms, regardless whether it is used on a bare metal target or it is used on a guest operating system. And there are some advanced features. For example, we have lists. We have our subscribers for the communication middleware, which we will learn in a later lecture, and so on. If you want to know something about the implementation, usually this is the way to go. So the source folder here. Then we have two ports for POSIX and for Macs to run your applications directly on the desktop computer. So the next folder here is the support folder. The support folder contains libraries and programs and tools that are optional. So they are not required usually in rodos applications or for rodos, but there might be need to use them. For example, if you want to have some mathematic library, this is implemented here. We have our matlib. We also have some random value generator. We have some communication protocols implemented here and so on. So that means you can just selectively include the code that you want to use. So just include the headers and use the CPP files here as well. The same goes for the programs. So usually you don't need them in your application. They are usually separate programs that can be run. And in your project, you don't need those. Maybe the middleware standalone, which is a middleware library that can be used without rodos. So for example, if you want to build a ground software, you can use this library in order to communicate with the rodos instance using the rodos middleware. But we won't go into detail here as well. Okay, then we have our test suite. So these are automatic tests that you can run every time you change something in rodos. So you in your project usually won't touch rodos, so you just include rodos into your project and compile against rodos, but usually you don't change rodos. But if you do, you can rerun the tests in order to see if something is broken. Then we have the last folder here, but not the least, because this is a very important folder for your learning right now. This tutorial folder contains different example applications that present different features of rodos. And I highly encourage you to have a look here. So it's sorted into different parts of rodos. For example, first step is, as the name says, for the first step to learn rodos. And there are also some compilation scripts for them. And I really encourage you to have a look here and also to modify the tutorials in order to learn how rodos works and how you can modify the tutorials in order to achieve what you want to achieve. So please have a look here into this tutorials folder. And then we have one important file for the compilation. We will see how this works. Yes, right now. Okay, so now let's have a look at how we can compile applications that use rodos. So I have mentioned the two options, CMake and shell scripts. So first starting with CMake, this is quite simple. The only thing you have to do is to download rodos and pack it to a folder, to a subfolder of your project. You can also use a git submodule, which makes it very easy to track afterwards. So you have to put it into your project, and in your project you're going to create a CMake lists file, which is basically the configuration for CMake for your project. The first two lines here are there for keeping CMake quiet because it complains if one of those lines are missing. So some project name, you can say whatever you want, and some CMake minimum required version number. Just put anything in that works. Then we have to make sure that we are using the C++7 version. This is required by rodos. So after that, you just add rodos at a subdirectory to CMake. And in this subdirectory, you see we have a CMake lists here as well. This is basically what is included there. You don't have to go into detail here. It just includes rodos appropriately. And then you can just add rodos executables with a name and a list of C++ files here. And basically that's it. When you compile, you also have to pass a CMake toolchain file, which is implicitly done here in Eclipse. If you do it manually, just keep in mind you have to provide the path to the port CMake file, which means it's at rodos CMake port and then the port that you want to use. For example, if you want to compile it for a discovery board, just use the discovery.cmake file. Okay, so this is one way to compile rodos, because that's it. Then you can just compile it. In the IDE, it's quite simple. Just press compile, and you can run it here as well in the IDE. So the IDE here is using CMake. This is also the advantage of CMake. You can just create your configuration once and then compile it again and again and again without have to pass every argument again and again. The other way is using the terminal. This is very, very good if you just want to compile quickly without the need to create some CMake file and so on. With these shell scripts, you just call the shell script and compile it right away. So let's do that here. First, open the terminal. So just menu here, the terminal. And here we just move to the directory that we have opened here. So this rodos template is the place where we want to go. When we start the terminal, we are in the home directory. And we want to change to this rodos template folder here. So use cd for change directory and go to Eclipse workspace, rodos template. And here we are. If we say list here again, ls, we see those are all the files that are contained in this folder. You see our CMake lists here. You see the build directory of Eclipse, our hello rodos, and the rodos folder. So we want to compile our application, our hello rodos application on the terminal. The first thing we have to do is we have to make the terminal aware of where rodos lives and where the shell scripts live. So first we change into the rodos directory. And you see here is this file, setenv.sh. That means this sets the environment variables that are needed to make the terminal aware of rodos. And we use this shell script by sourcing it. So we say source setenv.sh. So after pressing enter, you see this message. It says that now I know where rodos is. You may use the rodos shell scripts from anywhere and come back here using cd rodos. So that means we can now use the shell scripts to compile rodos and the applications. Okay, then let's move back to our application by going one level up. We are back in our rodos template folder, and now we can compile our executable. So the executable requires at least two parameters. The first one is the port that we want to use. As we are currently on Linux and we want to run it on Linux, I just say Linux x86, so for the x86 platform. And then we can pass a list of C++ files we want to include into the executable. In this case, we just want to compile the hello rodos.cpp, and we press enter. And that's it. If you do this the first time, there might be a message that the rodos library has to be built. So don't worry, this message is normal. If you execute this rodos executable shell script a second time, then this message, like at my place, does not appear anymore. Okay, what does this rodos executable.sh do? It uses the rodos library, compiles your CPP files and links them together into an executable. And if we have a look here, we see there is a new file which is called tst. And this tst is the executable that is created here. We can execute this executable by running /tst, so executing the file in the current directory, and just press enter. And we see something happened here. So you see the output here. We have output rodos. This is the rodos version that is used here. Some information about the rodos system here. We will get into these details later, at a later place. And down here, this is where the application actually starts. And we see it says hello rodos. So we stop rodos. Rodos is designed to run for infinite time. So usually on satellites, you start the application and usually you don't manually stop the application. So this is the reason why rodos acts in this way. So we need to kill the rodos application here. And you can do this by pressing Control, holding Control and pressing C. This stops the rodos application. Okay, so let's have a look. We had the output hello rodos. Let's have a look at the source folder, the source code, and we see we just have this printing scene here in the application. So these are the two ways of compiling rodos, either with a CMake file or with a shell script. The result is the same. It's just two different ways to accomplish compiling a rodos application. Okay, so let's have a look at our first rodos application. Basically, what you do usually is that you create threads. Threads implement tasks, for example, that should be accomplished periodically. And the API of rodos is designed in an object-oriented manner. That means most of the parts that you use of rodos are objects or classes. And this is also true for threads. In order to implement your own thread, you inherit from a rodos thread and implement your own behavior into your methods. So let's do it hands-on, and you can just keep following me and write it at your place, so to make sure that it's working for you as well. Okay, so we want to create a thread that periodically outputs some value, some text. So hello rodos, for example. This periodic execution is done in a thread. So let's create our own thread. We do this by creating our own thread class. So I call it hello rodos thread. As I just mentioned, this class has to inherit from the rodos class. There are different types of threads. The default way is the static thread, which means each thread has its own stack in which the thread runs. So every time a local variable is used or a new function is called or method is called, everything that is saved in between is written onto a stack. And if you leave the function or a variable is destroyed, the stack reduces again. And the static thread is programmed in a way that the stack memory is used statically. So it's as a member variable, a member array, it's saved. So that means if we create our thread in a static way, so global static variable, for example, that means that the stack is also kept there. Okay, so this was just a little bit too deep, I think. Just keep in mind, if you want to create a thread, just inherit from the static thread, and that's it. So we have read the static thread. The static thread is a templated class. The only parameter that you can pass there is the size of the stack. I think in most of the cases you don't need to care about this. So there is a default value, which has a quite good value. But if you run out of stack memory, just keep in mind set the stack size here, we just leave it as the default value. So just opening and closing those brackets here. Okay, so this is basically our thread, but we also have to implement what the thread actually does. So we're creating some public section, and then we override the run method. This is the method that contains the code that should be executed by the thread. It's quite easy. It has no parameters. It has no return type because we expect, so rodos expects that the run method does not return. So this is the usual way to do it. So it runs forever, maybe with some suspension in between. And yeah, so we just override the run method. And basically that's it. So we can also already do some printing here. Hello start. This \n is just for a new line. And then our thread can wait forever. Okay, this is our first thread. So this is only the class. We also have, of course, to create an instance of that. As I just have mentioned, we can do it like a static global variable here. Hello rodos thread, hello rodos thread. So having our instance here. And that's it. We do not need to register it into rodos in any way. The good thing here is we just need to create the instance, and it is automatically registered to the rodos scheduler. We do not have to manually register it by calling some function or method. So this is quite easy. We just create our subclass, implement the behavior, and create an instance of it, and that's it. So let's see if we have everything correct. We are compiling it, and we going to run it. As you see, we have here our hello start. Let's have a look to the output here. This is the default output of rodos, which gives you some insights into the internals of your rodos application. We have middleware. This is what we will cover in a later lecture, so just ignore this part for now. The thing that might be interesting for you is this list of threads in the system. You see we have one thread, which is named anonym thread, which has a priority of 100 and a stack size of 32 kilobytes. These are the default values. So 100, 32 kilobytes, and anonym thread. This is not very helpful, this anonym thread, for example, because it doesn't say anything about our thread. We can modify this. So we can give our thread a name that is printed right here in the output. In order to achieve that, we create our own constructor here and just call the constructor of the static thread. Maybe you have kept in mind that I said, okay, if you want to know something about how to use rodos, you can either have a look at the tutorials or just at the header files, and we can just do it. So I clicked with holding control on the name, then the IDE directly jumps to the constructor of the static thread. And there we see all the parameters that we can pass. So we have the anonym thread, the name, and we have the priority. And yeah, just let's change that. So the first parameter is the name. So let's just say hello rodos. And the second one is the priority. So compiling. and running it. Oh, okay, it's okay. So we see still the same output, but we have here now our hello rodos with a priority of 200. The value of the priority defines which thread should be executed first if we have two threads active at the same time. The one with the higher value that is passed here is executed first. So if we have two threads here, one with 200 and one with 100, and both are active, so ready to run, then the first one with 200 is executed first. Yeah, we will see later in an example. So as I have mentioned, we want to print periodically some output. And for this, we can use the time loop. The time loop is some nice macro that is provided by rodos. It looks like a loop as you know it from C++, but the purpose is a bit different. The purpose is to execute the body that is written here between the curly braces at given time points. The time point is defined with two parameters. The first one is the time at which the body is executed the first time. And the second parameter is the period. So starting with the first parameter, periodically the second parameter. Okay, just let's try it. For example, we have the first time every at 500 milliseconds since the start of the program. And then every 2 seconds printing something. Hello again. So it's called printf, of course, and it's called 500 milliseconds. Okay, so this loop in detail now starts at 500 milliseconds after the program has started, and every 2 seconds then this part is executed. That means every 2 seconds this hello again is printed. So the first execution happens at 500 milliseconds after the program start. The second execution at 2500 milliseconds. The next one 4500 milliseconds and so on. So let's try it. So hello start, hello again, every 2 seconds. This goes forever until we stop our rodos instance here. So stop it. So this is basically how you implement threads. So keep in mind, inheriting from the static thread class, overriding the run method, and implement the behavior there. So let's have a look at the timing. We already used some timing in form of the time loop. The internal representation of time in rodos is always nanoseconds. So everything comes down to nanoseconds. And the internal representation also uses the uptime. So that means time from starting the program or starting the hardware until now. And this in nanoseconds. There are different time literals which we already have seen. In order to express time, you can just multiply the value with some given name here. For example, you can define minutes. You can say, okay, I want to wait for 5 minutes. You say 5 times minutes, or seconds, milliseconds, and so on. And you see everything comes down to the nanoseconds. So finally, everything is translated into nanoseconds. You can at any given time, you can retrieve the current time with this small function that is called now. And as you might have guessed, this function just returns the current time since starting the program in nanoseconds. You can suspend the currently running thread for a given time by calling this at function. And important, as usually every value in rodos is it's an absolute point in time, so no time range. So instead of saying I'm suspending for 2 seconds, you say I'm suspending until a given time point. In this case, we want to suspend for 2 seconds, and that means we just have to retrieve the current time and just add 2 seconds there. And that means this method, so the thread is suspended at this method until this time point is reached. So the execution stops for this thread at this point, at this very point, and the function returns after the time point has reached. And suspending here means that the thread is marked in the scheduler as being suspended and other threads can run. We will see an example later. You can also suspend the thread forever. So there is also this special value end of time, which means just forever. So you might wonder, okay, if I sleep forever, so why do I actually need it? There is some common pattern which you use where you use that. So that means you sleep forever, but manually resume the thread, for example, from another thread. So you can always say a thread.resume in order to wake it up. So that means that this add forever is immediately returned and the execution of the thread starts again. So let's have a look at how scheduling works in rodos by a little small example. So in this example, we have 2 threads, one with the priority 115 and one with the priority 114. The idle thread is always there in rodos. So this is a default hidden thread that basically runs when no other thread is active. So in this scenario, we have the thread with a priority 114 running. The one with 115 is currently suspended. So that means this is running, this is suspended. So that means because the one with the higher priority is suspended, means that the lower priority thread is running. So it's running until the one with the higher priority is resumed. So that means this one is suspended, so implicitly suspended by the scheduler. Instead, this thread with the higher priority is executed until this thread voluntarily suspends itself. So for example, it might reach the end of a time loop and it's waiting for the next activation of the time loop. So after this one is suspended, the scheduler resumes the one with the lower priority. And this also happens going on. And this is also going on until the thread with the priority 114 also suspends voluntarily. So that means no thread is currently active, and as a consequence, the idle thread is running. Idle thread is running as long as no other thread is active. And it never suspends voluntarily. So that means when a thread is resumed, it's executed, And the only thing that makes this thread suspending non-voluntarily is if some event, for example, an interrupt happens. That means this interrupt is handled first, and after this is finished, the thread execution, so the normal scheduling is resumed, which means the thread 115 resumes until it suspends voluntarily. And after that, no thread is active, and consequently, the idle thread resumes. Okay, so let's see the scheduling in action. So just let's create two different threads that have different priorities. So I'm just taking my hello rodos thread and just copy it below here and just say hello rodos 2, just rename it hello rodos 2, and the same goes down here. So the hello rodos 2 shall have a priority that is lower of the one of the first hello rodos thread. So in the first we still keep the 200 priority, and the second one will get a priority of only 100. So, and in order to see what's happening here, we are just modifying the run method. So just starting over. I will just have an endless loop. And what we do here is we are just printing an A for the first thread, and we're going to print a B in the second thread. So just let's build our software. I'm going to use the shell scripts for building because we have to define the Linux x86 port. The configuration of the Eclipse is using the POSIX port, which means that not rodos own scheduler is used, but POSIX scheduler, and this is not behaving the same. We're just going to have a look here at building for Linux x86. So we say rodos executable. If you don't know how this works, just have a look back in this video. So rodos executable, and we are compiling hello rodos.cpp. So let's run it. We see only A's. There is no B at all. So why is that? So I'm just stopping with Control C. Why is that? Of course, we have both threads activated in the system, and if two or more threads are activated, the one with the highest priority is executed first, which means in this case the first thread is executed first. And this thread does not suspend at all. So it does not leave time for other threads to run. This is very dangerous if you use it in real applications, because basically you have only one thread then. If we just wait for some time, say we're waiting for 1 millisecond, that means that for 1 millisecond, the thread here, the hello rodos thread, the first thread, is sleeping for 1 millisecond, which gives other threads time to run. So in this 1 millisecond, the scheduler is able to run other threads. So just execute this again, and we will see we have A and a lot of B's, then a lot of B's. Though that means A is running first, then it's suspending for 1 millisecond, which gives B the time, or the second thread the time, to print some B's here until the first one is activated again. So the 1 millisecond is over, it's returning and executing this loop as well. And what you see here is the good thing about preemptive scheduling. So in the second thread, we are just having this endless loop and printing B. So we do not suspend the thread manually. The suspension in between, in order to give the thread A time to execute, is done by the scheduler. So the scheduler decides that it suspends this thread because there's another thread active, the first one, that has a higher priority. So this gets run first, and only if this thread suspends by itself, so either with an add or waiting for some input data or some interrupt data, something like that. That means only if the first thread is suspended, the other threads get the chance to run here. So you might wonder what happens if we have both threads on the same priority. So that means that we don't have a clear winner of which of those threads should be executed the first. Let's just try it. So first I'm going to remove the suspend command. So we have both threads with an endless loop. So no manual suspension at all. So save. I'm going to compile it and execute it again. And what do you see here? It's using a round robin mechanism. That means that both threads are executed one after the other. So the first one gets some time, the second one gets some time, the first one gets some time, the second one, and so on. This goes on forever. Okay, so this was a short overview about the scheduling, the priority preemptive scheduling of rodos. At the end of today's lecture, I have a small exercise for you that you should accomplish. All of those threads have a name that they should print periodically, and they should also print the current time at the given period. Each of those threads has a different period time. The first one is 1 second, the second one 2 seconds, the third one is 5 seconds, and the last one is 11 seconds. So please implement that and upload the source code of it. That was it for today. I thank you for your attention and see you next time.